In this video, we're going to talk about this idea of a squeeze theorem. So we're going to have certain situations that it's really kind of difficult to figure out what the limits are. This one, we're just trying to try to verify that it is. And so here's kind of this big idea that we're going to kind of look at Desmos and see how this relates to what we got going on. So if we have some sort of a function, right, and a is what we're trying to figure out the limit of, okay, and we are hoping it's some number, right? And so what we're going to do is we have this graph that we're not quite sure what. You have some sort of a function that when we zoom in a ridiculous amount, it looks relatively flat, let's say. And then this is going to be our g of x equation. Okay. And then we're going to not be able to find this value, but we're going to surround it with other functions that are going to converge. And so we're going to have this f of x that everywhere f of x is going to be less than g of x. Right? So this is our f of x function. And then we're going to compare it with another function that everywhere, make that a little bit better. Everywhere on this graph, h of x is going to be above, and they converge. Okay, so we're going to make it basically so that we're going to figure out how to create these equations that this function is always less than this function, and that function is always less than that function. But at a, we're going to actually make them all equal each other. Okay, so if these two functions equal that L value, then because everything is going to be less than, this thing sits right in the middle. So if those two things equal a certain value, 5, then that makes this one have to equal 5. All right, so let me show you kind of what this is in reality. So we're going to take this function and we're going to graph it. Okay, we're trying to verify that as x approaches 0, we're going to get this. The problem with 0 is can't plug in 0 because that makes this undefined. Okay, and so I don't know if it equals 0. And so we don't really have a way to manipulate it. We can't factor it. There's no radical that we can do a conjugate, none of that stuff. So let's take a look at the visual to this. Right, and so here is Desmos, and here's our equation. Okay, so if I take a look, it kind of starts to, who knows at this point. And so let's zoom in a little bit. Right, looks like it's getting infinitely small. So the visual is going to agree with that. But I need a mathematical way to kind of show this. And so what I can do with this is, let's go back, is this piece in general, let's just focus on this piece in general, is that a sine curve with no amplitude adjustment, we have no vertical stretch to it. I know that in general, whatever values I plug in is going to be somewhere between -1 and +1, right? That's just a sine curve. Just your basic idea. It's going to have somewhere between a -1 and a +1. All right. And so if I know that fact, I can create this in the middle. I can create an x squared by taking this whole thing and distributing an x squared to it. So that makes -x squared. Is then equal to x squared sine of 1 over x less than or equal to x squared. So there's our squeeze idea. This one's always going to be less. This one's always going to be more. And this is going to be somewhere in between. Right? So what we have going on is visually, we have this positive quadratic. We have a negative quadratic. And we have this sine thing, this sine curve, this thing that is doing that oscillating stuff in between. Right? So it's oscillating, but squeezing, and then it's kind of oscillating bigger. Okay, so that's us squeezing and trying to figure out and verify that it actually is going to happen. And so if I look at the visual, back to your graph again, right? And so let me turn that piece off. We have our lower function, we have our upper function, and we have that just that individual piece. right? Here's that thing. So it oscillates, and that's the one that's the problem. But if I do this, and if I start to zoom in, you can kind of see that it's just staying perfectly in between. And so it doesn't go outside of it, it doesn't go inside of it, like it just stays inside the entire time. And so if those problems are approaching zero, and that means, go back to the math, if we now do the limit as x approaches zero on the negative x squared, we know that that's approaching zero. If we do the limit as x approaches zero on x squared, we know that that's approaching zero. So by the squeeze theorem, squeeze theorem, our limit as x approaches zero for the whole x squared sine 1 over x has to be in between these two. And if they're both approaching zero, then this thing has to approach zero. And so usually these type of problems come up with one of these two pieces is the problem. It oscillates or it does something weird individually. And so then, but you can narrow what this idea is, and then you can bring in the other piece that's a little more straightforward by distributing it in. And then now, if we can do those limits approaching a very specific value, this value is going to be in between these two values, then we know exactly what's going to be happening to that. All right, and that was the squeeze theorem.